This is a graphical demonstration of required homework problem number 5, the merry-go-round. On the merry-go-round, a ball is thrown across a merry-go-round that's in the act of rotating, and the question is, will the ball follow a line that is an intuitive line that we see every day when we throw a ball on a field or any other normal surface? And the answer is that the ball will follow a curved path relative to the rate at which the merry-go-round is rotating. And this demonstration will show that quite vividly. So here we have two views of the same merry-go-round. At any given point, the two merry-go-rounds are completely identical. However, the one on the left will show the merry-go-round from a top-down view where the earth below the merry-go-round is constant and the merry-go-round itself is rotating. So as you can see, the merry-go-round rotates as time moves on. The view on the right, the camera is locked to the merry-go-round, so the ground below the merry-go-round will appear to rotate as well as a ball. So in both these images right now, the ball, the gray dot that's currently on the red dot right now, which represents Peter, the ball is thrown straight up, and as time moves, the merry-go-round will rotate at 120 degrees per second. So after 3 seconds, it will complete one revolution and be at the same location. And you can see at any given point, the ball is in a fixed position relative to the ground and is moving relative to the merry-go-round. Alright, so we can also have the merry-go-round be stationary and have the ball move with respect to time. So the ball will always move from Peter to Danny. Peter throws it to Danny, and as time moves on, it'll move in a straight line towards Danny. So you can see on the left, it is a perfectly straight line, and it ends up right at Danny. We can do both these things at the same time, and this gets to the real demonstration of the problem. If we set this to the same value, 120 degrees, and we play this, we can see on the left the ball is moving in a straight line while the merry-go-round rotates below it. And on the right, it appears as though the ball follows a curved path relative to the two people. During the time that the ball is in flight, the merry-go-round rotates exactly once, and Danny catches the ball after having moved around the merry-go-round during the duration of the ball's flight. We can plot the path that the ball follows across those 3 seconds, and we see that relative to the ground it is a straight line, and relative to the rotating merry-go-round it follows this curve looping around. So we can follow this through the time. Remember, at any given time these two images are exactly the same. So we can see relative to the red dot, which represents Peter, the ball is moving away from him. According to both these views, you can look at the left view and you see it's moving away. Right here it's at about its maximum distance, and then the distance between them starts to shrink again. It gets to a minimum distance of right about here, and then starts to move away from Peter again, and eventually moves away to a maximum distance and is caught by Danny. We can update any of these values with the path still being plotted to get some interesting results. So I'm just going to make the merry-go-round rotate faster and see what that how that changes the path of the ball. So I'm going to turn this from 120 up to, let's say, 170 or so. We see that has created a different shape for the ball, and we can also update the positions of the two people on the merry-go-round. So I'm just going to move Peter here. How about here. So now it appears as though the ball, as time moves on, moves away from Peter, comes back towards him, appears to stop momentarily, freeze in the air, reverse directions, move away from Peter again, and then come back around to his right, eventually coming back right to him. A very strange effect when you consider that Peter threw the ball directly at Danny, and yet it came right back to him, and he can catch it right again. So this is the sort of dynamics that are under effect when you have a rotating reference frame. So the curved path that the ball follows when the surface below it is rotating is caused by a force called the Coriolis force. And the Coriolis force is an inertial force, which means that it's not a force caused by a specific interaction between objects, such as a collision or electromagnetism or some other force caused by inherent properties or situations of objects. Instead, the Coriolis force, like many other forces such as the centrifugal force, is caused by a specific situation that the object is in this case a rotating reference frame, but that doesn't make the force any less real. If you're on a merry-go-round, just like you will feel the centrifugal force pushing you outwards, you're going to feel the Coriolis force if you're walking along the merry-go-round or throwing a ball or any other kind of movement. The force is very real and can easily be used and taken advantage of. It has many real-world applications and also is the cause of many real-world things such as weather or other things taking place over large distances where the rotation of the Earth or rotation of other objects can have an effect. So I think this is a good demonstration of the Coriolis force. And I definitely had fun making it, so thank you for watching.